Hello everyone, my name is Mathieu Collet. I'm working at Similar Research Laboratory, which is located in Oslo in Norway. I also work in collaboration with ABB Robotics for testing industrial robots. The goal of my research is to develop a new tool named RobTest. This tool is a constraint programming approach to generate maximal test trajectories for industrial robots. Nowadays, developing industrial robots which are safe, performant and robust is a challenging task. The goal of generating test trajectories is to increase the chance to uncover potential failures. These failures can be a software or an hardware problem inside the robot. Currently, these test trajectories are manually created by test engineers. Once the test is written, it can be launched either on a real robot or a simulated system. After the execution of this test, the test engineer can have a look to the test output, error messages, or data coming out from the robot in order to detect if there is any problem inside this robot. But with this system, when a test is created, this is always the same test that is executed on the robot. So with our new approach, we would like to automatically generate these test cases and also to produce several different tests in order to execute all these tests on the robot and not only one. And the goal will be to generate optimal test cases. Our contribution is a new tool named RobTest. This tool is able to generate test scenarios with high resources usage. The generation of these test scenarios is something challenging in the robotic domain because you should take into account several different parameters like the robot motion, robot speed, or the environment around the robot. RobTest is an intelligent process using constraint programming and optimization in order to generate test cases. A test case is a test program performed by a robot. So you have an example of test cases at the screen in which you have several motion instructions. Our new approach is using two constraint solvers. A solver over continuous domain for modeling the robot workspace and a solver over finite domain in order to generate maximal load test trajectories. Hello everyone, my name is Mathieu Collet. I'm working at Similar Research Laboratory, which is located in Oslo in Norway. I also work in collaboration with ABB Robotics for testing industrial robots. The goal of my research is to develop a new tool named RobTest. This tool is a constraint programming approach to generate maximal test trajectories for industrial robots. The first part of this presentation is a stress testing of industrial robots. Nowadays, developing industrial robots which are safe, performant and robust is a challenging task. The goal of generating test trajectories is to increase the chance to uncover potential failures. These failures can be a software or an hardware problem inside the robot. Currently, these test trajectories are manually created by test engineers. Once the test is written, it can be launched either on a real robot or a simulated system. After the execution of this test, the test engineer can have a look to the test output, error messages, or data coming out from the robot in order to detect if there is any problem inside this robot. But with this system, when a test is created, this is always the same test that is executed on the robot. So with our new approach, we would like to automatically generate these test cases and also to produce several different tests in order to execute all these tests on the robot and not only one. And the goal will be to generate optimal test cases. Our contribution is a new tool named RobTest. This tool is able to generate test scenarios with high resources usage. The generation of these test scenarios is something challenging in the robotic domain because you should take into account several different parameters like the robot motion, robot speed, or the environment around the robot. RobTest is an intelligent process using constraint programming and optimization in order to generate test cases. A test case is a test program performed by a robot. So you have an example of test cases at the screen in which you have several motion instructions. Our new approach is using two constraint solvers. A solver over continuous domain for modeling the robot workspace and a solver over finite domain in order to generate maximal load test trajectories. As I said before, testing industrial robots is important to detect faults into the robot. So here you have an example of deviation scenario. So when a test engineer is writing a program, is set up points into the working space, and all these points create a trajectory. Here in blue you have the trajectory which is specified into the test program. And during the execution of this test, the robot is following this program. But you can find a small deviation between the specified trajectories and the actual trajectories performed by the robot. So the goal of RobTest is to create the test program that can be run on the robot and to detect the deviation between the specified trajectories and the executed trajectories. The following part of this presentation is a presentation of RobTest, a CP-based method for generating maximal test trajectories. The goal of RobTest is to find a trajectory into the working space of the robot. So for this, we have a modelization of the robot workspace. As you can see, we have the unreachable zone, which is a zone in which the robot cannot move due to a mechanical constraint. All the gray zone is a working zone in which the robot can move. Inside this zone, the test engineers can put obstacles in blue, O1 and O2, and several points. And the goal of RobTest will be to find the trajectories between the starting point and the ending point, avoiding all the obstacles and unreachable zone. Here you have an example of the trajectory generation. So inside the working space you have 6 points and 2 obstacles. And the goal will be to find a trajectories going from the starting point P1 to the ending point P6. For example, you can have these trajectories going from P1 to P6 through P2, 3, and 5. And the load of these trajectories is 40. To find the load is the sum of individual load on each edges of the trajectories. So in this case, 5 plus 10 plus 10 plus 15. And the goal from this is to create a test program. This test program is a motion instruction for the robot. From this, you can also have a different trajectories. Now we are going from P1 to P6, but through P2, 4, 3, and 5. And because the trajectory is different, we have a different load on the trajectory. Now it's 60. And the goal is to create another test program, which is different from the previous one. And the goal is to find optimal trajectories based on the load of these trajectories. To do this, we use two constraint solvers. The first solver is over continuous domain, and the second solver is over finite domain. So RobTest has two different components. The first component is responsible for the reachability problem. So this component is using RealPaver, a solver of a continuous domain, for modeling the robot workspace. For the modeling of the robot workspace, we define all the constants, like the position of the point and position of obstacles, and we define also the equation of the robot workspace. So in yellow, you have the equation for the envelope of the robot. In red, you have equation for the unreachable zone. And we also define equation for all obstacles that the test engineers put into the working space. And the goal is for each pair of points given in the initial cloud of points to know if these points are reachable or not. So for doing this, we have several steps. The first step is the modeling of the working space and the forbidden zone. Forbidden zone is the unreachable zone and all the obstacles that test engineers put into the working space. And for each pair of points, we will call RealPaver several times to check the reachability between these points. The first call is to know if the points are inside the working space. If they are inside the working space, we have a second call that is checking if the segment between these 2 points is crossing the unreachable zone. If the unreachable zone is not crossed by the segment, we have a third call. And this call is a loop. For each obstacle, we are considering the segment between the 2 points, and we are checking if this segment is crossing one of the obstacles into the working space. If at the end of all the execution there is no solution returning by RealPaver, this means that the 2 points are reachable, and we can add these edges inside the reachability graph. And once all the execution of RealPaver over all pair of points is done, the graph is created, and we know all the transition between all the points into the working space. So the output of the first component of RobTest is a multi-load labeled oriented graph. Once the reachability graph is generated from the first component of RobTest using RealPaver, we are able to calculate the load for each transition on the graph. The load value is taking into account 2 parameters, the distance between the point and its successors, and also the angle between the predecessor, the node, and the successor. So you have an example on the left, taking into account one node, Pj, one successor, Pl, we will have 2 different load value, between Pj and Pl, depending if we are coming from Pi or Pk. And with the same distance between Pj and Pl, we'll have a higher load value if the angle between the predecessor and the successor is more acute. So you have an example on the right saying that, for example, if we are going from the node 2 to the node 3, if we are coming from 4, the load of the trajectory will be smaller than if we are coming from 1, because the angle between 1, 2 and 3 is more acute than 4, 2 and 3. Now let's move to the second component of RobTest, which is responsible for the trajectory generation. So this part of implementation exploits the constraint programming over finite domain. And for this, we use Minizinc with 3 different solvers. To do this, we get the reachability graph from the first component, and this graph have nodes and edges, and we created variables for each node. So the first variable is the successors of the node. The second variable that we create is all the predecessors of the node. And the last one is the load of switching from one point to its successors, taking into account all the predecessors. And the goal is to find the optimal trajectory starting from the starting point until the ending point. The implementation of the second component inside Minizinc uses different constraints. The first constraint is that the successor of the ending point is the starting point, and the predecessor of the starting point is the ending point. By this, we have a loop, we have a circuit. The second constraint is inverse of successor and predecessor. That means that, for example, if we consider a node I, if the successor of I is J, the predecessor of J should be I. And the third constraint is subcircuit. That means we are looking for a circuit into the initial cloud of points. The fourth constraint is the table constraint. It's taking into account the node, the successor of this node, the predecessor of this node, and the load of the transition. It's also considering the load relation, which is taking into account the same parameters. The goal of this table constraint is to give the valid combination of node to visit, its successors, and its predecessors. And it also acting as a partial function for computing the relevant load for specific combination of node successors and predecessors. And the main objective is to maximize the load relation in a trajectory going from the starting point 1 to an ending point n. So you have the maximize function at the screen. The implementation of this. So actually, a test engineer is writing a test program, and this test program is run on a simulated system or real robot. And with this new approach, we would like to remove the manual writing of these test trajectories using RobTest. So for this, you have RobTest, which is divided into 2 components, the configuration reachability, which is made by real power, and the second component, which is a trajectory generation made by Minizinc. So the test engineer is selecting and setting the points, obstacles into the working space, and RobTest is generating this test trajectory program. And from this, the program can be launched in the simulated system or a real robot. To do this, we have created an interface to help engineers for generating test trajectories. Inside this interface, the test engineers can select the robot type, and depending on the type of the robot, we are modeling the working space of the robot. We also have the unreachable zone. From this, the test engineer can set up different obstacles in blue and a cloud of points in red. Here you have two different possible configurations with all the points and obstacles. So this is the entry point of RobTest. And from this, we can execute the first component of RobTest to generate the reachability graph, because we can see that different points cannot be connected because they are crossing the unreachable zone or some obstacles. And from the first execution of RobTest, the first component, we get the reachability graph. And from this, we can run the second component with minizing for searching test trajectories into this graph. So the last part of this presentation will be the experimental evaluation. For the evaluation of RobTest, we define a specific protocol. So the test engineer are setting points and obstacles into the user interface. From this interface, the first component of RobTest can be run. This component is using real power, and we create 14 instances from 15 to 100 points. The medium density of the generated graph are between 4% and 10%. The second component of RobTest is generating the optimal trajectory using minizing. During the evaluation, we compare three different solvers. The first solver is G-code, the second solver is Shuffled, and the last solver is Sixtus Prolog. We define an overall timeout of 5 minutes for the generation of trajectories. If in 5 minutes the optimal solution is not returned, we get the current solution. All these experiments have been executed in all instances, but for the sake of simplicity, we present only the result in one instance, which is representative for all solutions. Also, all the different instances are available on my GitHub, and you have the address at the bottom of this slide. The first evaluation is a comparison between different variable heuristics. For this, we selected 9 different heuristics that we run on 3 different solvers: Shuffled, G-code, and Sixtus Prolog. This experiment was run on all instances, so the 14 different instances, but we present only the results of instance with 55 points. These results are representative of all the results that we get. On the first part, we focus on the first solution. So you can see that all solvers are able to return a first solution in less than 1 second. Also, the quality of this first solution is higher than 80% in most of the cases. But with max regret, the 3 solvers are able to return a first solution with a quality higher than 88% to the optima. Also, in terms of time execution, we can see that with max regret, we get one of the smallest time execution to get the first solution. The second comparison is over the best solution. So you can see the red line. This is a timeout of 5 minutes. And from this, we can see that all solvers are able to return a best solution with a quality higher than 95%. Also, most constraint and max regret are able to return the optimal solution in less than 5 minutes. And in terms of time execution, we can see that max regret is the most interesting heuristic because we get the optimal solution with the smallest time execution. So the most interesting heuristic for RobTest is max regret, whichever the solver we use. The second evaluation is a comparison of the 3 solvers: G-code, Shuffled, and Sixtus Prolog. from the same result on the same instance, we can see that to get the first solution, Sixtus Prolog have a higher time execution to get the first solution than Shepherd and G-code. So Shepherd and G-code are competitive to get the first solution. And for the best solution, so we can see that Shepherd is better than all other solver for all different heuristics except most constraint and first fail. But using max regret, either for the first solution or the best solution, Shepherd get better solution. So for our new approach, using max regret as a heuristic and Shepherd as a solver, we get the best performance. The last experiment is the evaluation of RobTest. For this, you can see the table with 14 instances and the 3 different solvers, Shepherd, G-code, and Sixtus Prolog. These results are obtained with the max regret heuristic. You can see that for small instances, from 15 points to 40 points, the 3 solvers are able to return the optimal solution in less than 1 second. However, the size of the search space to find the optimal solution is smaller with Shepherd than G-code and Sixtus. You can see this with the column of number of fail. So for small instances, Shepherd is better than G-code and Sixtus. Let's move to the medium instances from 45 to 55 points. As you can see, Shepherd is able to return the optimal solution for the 3 instances in less than 23 seconds, which is better than G-code with 28 seconds and Sixtus with 76 seconds. So for medium instances, Shepherd remains the winner between the 3 solvers. For the large instances, from 60 to 100 points, Sixtus are not able to return the optimal solution within 5 minutes timeout. So Sixtus is less competitive than Shepherd and G-code. And the comparison between Shepherd and G-code, you can see that Shepherd is able to return the optimal solution until an instance of 80 points. During this time, G-code is only able to return the optimal solution until an instances of 80 points. So in terms of quality of solution, Shepherd is better. Also, in terms of the size of the search space, Shepherd have a less number of fail than G-code for the large instances. You can see this, for instance, 60 and 70. So for the 3 kind of instances, a small one, middle one, and large one, Shepherd is the most suitable for RobTest. And the quality of the solution returned by Shepherd is good enough within 5 minutes until 100 points. To finish my presentation, I will present the conclusion and the perspective. To conclude this presentation, I presented a new approach named RobTest using constraint programming. So in this new tool, we had 2 different constraint solvers, one over continuous domain for generating the reachability graph, and another solver over finite domain to find the load optimal trajectories into the reachability graph. So the results show good enough quality solution for deploying RobTest into a continuous integration process at ABB Robotics, because we are able to return solutions for graph with more than 80 points, and also the quality of the solution is a good quality with this short time contract of 5 minutes. We are able to get almost the optimal until 80 points, and more than 80% of quality solution until 100 points. The perspective of the work is to improve our model by including more parameters inside the load function, because at the moment the load function is only calculated with the distance between points and the angle between the predecessor, the point, and the successor. We also would like to have a new comparison between a new version of Sextus Prolog, which include the subcircuit global constraint. We also want to deploy RobTest at ABB Robotics and put RobTest into the hand of the test engineer in the more regular basis. Thank you for your attention, and now if you have any question,